So we did solve one-dimension heat conduction problem using the analytical solution, right? Heat conduction analytical solution. And the problem statement or the design that we got before is a solid bar of thermal conductivity K is equal 10 watt per meter Kelvin. The bar has a total length of 0.6 meter. One face is exposed to a temperature of 100 degrees C. The other end is at a temperature of 20 degrees C. And these are Dirichlet boundary conditions. And we did the design. We made the assumptions. Actually, we got the models first, right? We got our model, correct, which was the heat diffusion equation. And we simplified the model to end up having the Laplace equation. So the model started from heat equation. And after simplification, we end up to have Laplace equation. And the which ended to be partial 2t by partial x squared is equal 0, square equals 0, after assuming there is no heat generation and it's a steady state problem. And we were able to solve, and we got the analytical solution for that problem, that t as a function of x is equal to minus 133.3 x plus 100. And we showed that the temperature distribution is simply a linear. This is where x is equal to 0.6. This is the x direction. This is 100 degrees C. This is 20 degrees C. This is my temperature as a function of x. And the change of temperature is coming to be linear within that domain. This is the analytical solution. Now, I would like to do that using the CFD technique, discretization technique. I would like to approximate that and numerically solve the problem. Again, we are focused on the finite difference method here. So I'm going to solve using finite difference method scheme or approach or approximation. Discretization method to find the temperature distribution along the bar. Okay, so instead of solving analytically, we're going to solve that numerically. So to do the numerical solution, we have to do the discretization, which means you have to start with gridding and meshing your domain, right, to determine where are the nodes. Then you're going to apply the approximation of that model using finite difference method. Either you are using forward, backward, or central method, right? And solve the algebraic equation to get your answer. So let's see the steps to solve that one-dimension heat conduction problem. So we are solving one-dimension heat conduction numerically. So my first step, I'm going to pick up my domain. This is my x. Then I will break down my domain into subdomains. So what I'm going to do, I'm going to divide my domain into pieces. So what I'm going to do, I'm going to select that my delta x or h spacing, h or delta x to be 0.1. This is 0.6 meters, so I'm going to have 6 subdomains, right? Here's 1, 2, 3, 4, 5, and 6. I'm trying to be in an equal, but I'm using my hand drawn right now. So this distance here is 0.1. This is also 0.1. It's 0.1, 0.1, 0.1, 0.1. And this distance here, you call it h, you call it delta x. I prefer to call that delta x, right? So if you do that, we are solving one dimension. So I'm going to end up having one node in here, one node in here, one node in here, one node in here, one node in here. This face is 100 degrees C. this face is at 20 degrees C, and I would like to get the temperature at these nodes. And I believe that having 5 data points inside that domain is enough to present all the details, okay? Or reveal all the details about the temperature distribution, okay? And again, remember, boundary condition is very important. We're having Dirichlet boundary condition. Your solution has to be within these boundary conditions. So any one of these nodes, if you got a temperature lower than 20 or higher than 100, with the setup that we have for this specific problem, you did something wrong. So let's number the nodes as part of the procedure. I'm going to call this node 1, node 2, node 3, node 4, node 5. You can write it down in a different way. You number them in a different way, but I'm intentionally doing that in a reverse direction, so your brain becomes more focused when you apply the equation. So we have 3 choices when we apply the again, design. That's my domain. My model is still the equation. Now I would like to solve, but instead of solving analytically, I'm going to solve numerically. So the first step under solving is to divide your domain into subdomains, meshing and gridding. I numbered my nodes. Now I need to do the discretization. I would like to convert the equation into algebraic equation. You notice that the analytical solution, or the model that we are using here, only contains the second derivative, which means that I would like to pick one of the second derivative approximation of the finite difference method. You can use backward, you can use forward, you can use central. In this example, I will use the backward finite difference method. Then I will let you practice using the central finite difference and see and compare the results I'm getting into this one and the central. Central finite difference is much easier because, again, if you look back into the recording of the approximation and the generalization of the finite difference central method, it's just you need one node before and one node after, and you apply that. So let's recall what's the approximation of the second derivative for the backward. So I'm going to use backward finite difference method here, and I will let you practice the central finite difference method and compare the results. The second derivative of the backward finite difference method mentioned that f of x minus 2h minus 2 of f x minus h plus f of x divided by h squared. And if you recall, we had an error of an order h for the backward. Okay, so to apply that equation, I need the base point. That's my base point. 1 point, first point backward, second point backward. So for example, if my base point is node number 1, I'm going to need node 2 and node 3. If your base point is node number 2, you're going to need 3 and 4. If your base point is node number 3, you're going to need 4 and 5. If your base point is 4, you're going to need 5 and 100. And I cannot use the backward finite difference method for point number 5 because I need 2 points backward. I have only 1, so it doesn't apply here. So let's see how we're going to do that. Can you use it for node 20? Yes, I can, because I have 2 backward nodes here. So this application of using the backward finite difference method can be applied for the node of 20, 1, 2, 3, and 4, but I cannot use it for node 5. How many unknowns we have in this problem? We have 5 unknowns, so I need 5 equations. So I need to apply this approximation to 5 different points to get 5 algebraic equations. Then I will solve this equation together. And it seems to me that these points are obvious now. I'm going to have the face of 20, node 1, node 2, node 3, and node 4. Let's apply that backward finite difference method and see what the algebraic equation going to look like. So if I would like to apply that for the face of 20, okay, I'm just going to keep this side to side so you guys can see what I'm doing. So let's apply that at the face of 20. So this equation is telling me that the second derivative, right, at that face is equal to the second node before, which is number 2, minus 2 of the node before, which is node number 1, plus the value of the base point, which is 20, divided by 8, h squared, right? This is what the equation. But according to this equation, that derivative should equal to 0. So f of x minus 2h minus 2f of x minus h plus f of x divided by h squared should equal to 0. So that denominator will go away. So f of I minus 2 minus 2 f of I minus 1 plus f of I equals 0. This is the general form of the equation, right? So if this is your I point, if this is the I point, right? So this is I minus 1, this is I minus 2. Again, let me write it down. If this is the I point, this is I minus 1, this is I minus 2. So all what you need to do to replace I minus 2, this will be the temperature at node number 2 minus 2 of the temperature at node number 1 plus the temperature at the base point, which is 20 degrees, equals 0. So this is at the right boundary condition. Okay, now let's apply that at node number 1. So at node 1, what you are getting, this is now becoming your I point. This is becoming I minus 1. This is becoming I minus 2. So this equation is telling me the temperature at I minus 2, which is T3, minus T2 of T2 plus the base point is now point number 1 is equal to 0. What about node number 2? For this is my base point now. This is I minus 1, this is I minus 2, right? This is I. So I will have temperature at node 4 minus 2 of the temperature at node 3 plus the base point is T2 is equal to 0. What about node 3? This is my I minus 1, I minus 2, temperature at 5 minus 2 temperature of 4 plus temperature at 3 is equal to 0. Then I'm going to go for node number 4. This is my I minus 1, I minus 2. So I will have 100 minus 2 of T5 plus T4 is equal to 0. Now I have 5 equations and 5 unknown. I cannot apply at node number 5 because I have only I minus 1, I don't have I minus 2. I cannot invent that. I cannot say that it's 100 degrees like that phase. It's outside your domain. You cannot use anything outside your domain. So you end up having 5 equations in 5 unknown, which is T1, T2, T3, T4, T5, and this is what I'm looking for. Now, this is what we call the discretization. This is how I converted the second order homogeneous differential equation into a system of linear equation. I can solve these equations very easily. There are many ways you can solve this equation. The simplest one is to use the matrix way. So let's construct the matrix. Remember, system of linear equation, it's AX equal to B. This is how you solve that, right? You can do that manually. You can do that using MATLAB. Feel free to do whatever you want. There is online solution of system of linear equation. I prefer you to go into MATLAB, set up your equation. So if you want to get the X, you're going to get A minus 1, the inverse of the matrix A times matrix B. And this is just take like 15 seconds on MATLAB to do that. First, you have to set up your equation in a correct way. So this is a coefficient matrix times the variable matrix equal to the free term matrix, right? So let's set up that. So I have T1, T2, T3, T4, and T5. Let me draw just for those doing that for the first time. I doubt that should be a very fundamental thing to do. Now, try to be organized when you put your data. So now, let's take the first equation. I will take, it doesn't matter which one you take. So let's actually take node number 1 here. I will consider that, actually, it doesn't matter. Let's go in order. So I'll take the first equation. So T1 has a coefficient of -2. Then T2 has a coefficient of 1. There is no T3, so the coefficient is 0. There is no T4, that's a coefficient of 0. And there is no T5, I need another one here. So the coefficient is 0. Then the free term will be minus 20. Now go to the next equation. T1 has a coefficient of 1. T2 has a coefficient of minus 2. T3 is 1. 0 T4, 0 T5, and the free term is 0. Next equation, T3 is a coefficient of minus 2. T2 has a coefficient of 1. T3 has a coefficient of, sorry. For that node, T1 is 0 actually, sorry. T2 has a coefficient of 1. T3 has a coefficient of minus 2. And T4 a coefficient of 1. Then I have 0. The next equation, 0 T1, 0 T2, 1 T3, minus 2 T4, 1 T5, then 0, 1, 0, 2, 0, 3, 1 T4, minus 2 T5. The free term is always 0, 0, and the last equation will be minus 100. This is your matrix A. This is your matrix X that you're looking for the value, and this is your matrix B. Set up the matrix in MATLAB, then you solve. I got the following equation. I got T1 is equal to 33.33. T2 is 46.67. T3 is coming to be 60 degree. T4 is coming to be 73.33, and T5 is equal to 86.67. So logically, we got 100 degree here, got 20 degree here. Then you notice that 33.3, 46.67. I'm going that direction, right? So the nodes is going that direction. This is at node 1. This is at node 2. This is at node 3. This is at node 4. This is at node 5. So you'll find yourself actually getting a linear distribution for the temperature, which is really good. Again, you are bounded by the boundary condition. You are somewhere between 20 and 100. You cannot be less than 20. You cannot be more than 100. And I did actually a very simple block. Let me find that solution here. Look at this. This is showing the analytical solution, the function I get analytically. And these are the values that I got with the backward finite difference. It seems to be perfect. It's really very good. So the error is almost nothing, right? I'm matching well with the analytical solution. So that's how it looks like. Now, I would like you to use the central finite difference method instead of using the backward, right? So this approximation has to change. So let me write down the equation for you before you go and practice that. So that's a practice exercise. So f double prime is equal to f of x plus h minus 2 f of x plus f of x minus h divided by 2h, by h square or delta x square. Let's keep it h square. This is the approximation of the second derivative using central finite difference method. So instead of using this formula, you're going to use this formula. You call your I point, you construct the 5 equations, then you solve. Then you can compare what you got for using the central finite difference method compared to the backward finite difference. This is just a proof on number 1, both are working fine. Number 2, you get the sensation if there is really a change in the final values, because we know that the order of the error here is different than the order of error here. But maybe for this problem, you don't get that sensation, that measurable error difference, but you need to practice that and look into it. And that's conclude the one-dimension heat conduction example using the backward finite difference method.